Yeah, 23.
Yes, on number 23, you're given the problem x times the square root of 4 minus x, and you're just asked to find the local extremum. I just wasn't sure how to do it without.
So careful here in what's your domain, because you can go chasing stuff. Remember, because this 4 minus x is in the radical, and we know that 4 minus x has to be greater than or equal to 0. So we're really only interested in values of x that are less than or equal to 4. But now we're going to do the whole take the derivative, set it equal to 0, and number line thing.
I wasn't sure how to set it equal to 0 after I.
Oh, okay. So for derivative purposes, we're going to think of that as to the 1/2. There's a product rule derivative, so we go first, and now we're going to chain rule. So we're going to have 1/2 times 4 minus x to the negative 1/2 times the derivative of 4 minus x, which is -1, plus the second 4 minus x to the 1/2 times the derivative of the first, which is just 1. And we're going to set that equal to 0. Yeah, so the tricky part. Now, what we're going to do is we're going to factor out the smaller of the exponents and the least common denominator just to make it nice. So we'll pull out 1/2, and we're going to pull out this 4 minus x to the -1/2. Okay?
Yes.
So that's going to leave us with, we got this negative, we got an x.
And we can do that even though one of them's the -1/2 and one of them's the +1/2?
Yeah, so yeah, and the key is, I mean, when you pull out the smaller of the exponents, it's always going to work the best. And so that's the whole key. And then if you just follow that rule and then, proceed on faith, it'll work out well. So here, when you take out the -1/2, remember, when you factor something out, you're dividing by that thing. So you're dividing by, right? So if you had, say 5x minus 10, you factored that 5 out, you're dividing this 10 by the 5.
Yeah.
Okay, so when you factor out the 4 minus x to the -1/2, you're dividing by that -1/2 exponent. And to divide by a -1/2 is to add that exponent. So this is going to just become 4 minus x to the first. And now things are looking good. So this all goes to the denominator. So there's your 2 square root of 4 minus x. And then this we just clean up a little, and it looks like I think 4 minus 2x. So when we're looking for critical points, it's kind of nice when you have it as a fraction, because it will be equal to 0 when the numerator is 0. It'll be undefined when the denominator is 0. So you're going to get 4 minus 2x is 0. 4 is 2x, so x is going to be 2 is one critical point. And this will be 0 when x is equal to 4. But that's, I guess that could still be a relative minimum or maximum in our scheme. So let's see what we got. So we're going to look at our derivative, and our domain is going to be x less than or equal to 4. So we're looking at something like that. Is that okay? 4 is right there. 2 is going to be somewhere to the left. And so if we plug in something like, say, 0, then 4 minus 0 is positive. It's going to be a positive always in the denominator, and a positive divided by a positive is a positive. When you plug in, say, 1, this is going to be, is that right?
I got a
3.
point.
What's that?
I got a different critical point.
Uh-oh. What did you get?
8/3.
Did I do this wrong somehow? Did you get the same derivative that I did?
Yeah.
Did you get this as a derivative?
I didn't know, not like, I just subtracted the negative section, like the left side of your equation to the other side
Okay.
to solve it.
So you said that, so that becomes positive when you add it to the other side.
Yeah.
So you have x over 2 square root of 4 minus x is equal to this square root of 4 minus x. Is that correct? So where'd you go from there?
Multiply the denominator. Multiply 3 by 4 minus 4. Or square root
Square root of 4 minus x. So that'll cancel here. And you'll get just 4 minus x there. Is that correct?
Yes.
Okay,
and then multiplied by 2.
okay, so that's going to be x equals 8 minus 2x. Oh, how do we do that? You see? I don't see anything wrong with that. What, did I do something wrong here? So we agreed on the derivative part, so I factored out the 1/2.
So when you multiply, do you add exponents? So like,
Yes.
wouldn't inside your brackets, I thought it would be 4 minus x quantity squared.
Oh, you know what, no, I don't think so.
No?
But I think when I factored the 1/2 out, I didn't account for that here.
Oh.
So that needs a 2. So there was my mistake there. You are right, Reese. So this is going to be 8 minus 3x like what you did. And so we are going to get the same thing, that 8/3. So we're going to have the 8 minus 3x equals 0. So 8 equals 3x. So x equals 8/3. Macy, actually, what was your question? Do you want to make that squared? Or?
I'm confused about the like when we factored out or pulled out the 4 minus x to the negative 1/2.
So another way of thinking is, let's see what happens when we distribute and get back. So we should be able to distribute this.
Oh, just kidding, never mind.
And, okay, you see it? And get back to where we started.
We good now.
Okay.
I can do
All right.
simple addition.
Okay, so I think you might, did you get this one, Macy Carlson?
4?
The 4 as a critical point?
Yeah.
Okay, good. I think we're in business. So this is not going to be 2. This is going to be 8/3, which is 2 2/3. So I think we're still okay over here plugging in 0 and still getting a positive over a positive is a positive. So I think we're there. And if we plug in something like, say, maybe 3 here, now this is going to become a negative, but this is always positive because we can't get a negative out of a square root. So positive over negative will be positive. So we're going to get a relative, it looks like, maximum at to the, I'm going to get an order pair, 8/3, going back to the original f of x. So this is going to be 8/3 times the square root of 4, which is 12/3, right, minus 8/3 is 4/3. Yeah, miserable. So that's 8/3. That's going to be square root of 4 is 2 over the square root of 3. So we'll call that 16 over 3 square root of 3 for relative max. Now, if it's going to decrease down to 4, so the function is decreasing to that endpoint at 4, then that's going to make 4 a relative min or relative max. Relative min. So we're going to get a relative min at 4, and we plug in 4. 4 minus 4 is 0, square root of 0 is 0, 0 times anything is 0. It's going to make that be 4, 0. That okay? That was a good question.
I was honestly expecting you to just say, no, you have to graph this, but
Oh,
no. This is good to learn.
Anything else?
Should have graphed it.
Okay, so we're going to talk today about linearization, Newton's method, and differentials, all in 19 minutes. A daunting challenge. So the idea here is that a differentiable function is what we call locally linear. So a differential or a differentiable function. is locally linear. So what we mean by that is by the nature of it being differentiable, it does not have a corner, a cusp. Vertical tangent is not really a big deal, but it doesn't have a corner, cusp, or discontinuity. So for example, if you think of something like, a sine curve, something like that, and pick any point you want on there, even though this is pretty curvy as it goes, if you were to like zoom in with your calculator and get close enough in there, if you get close enough, it looks on your screen like a little piece of that anyway, looks like a straight line. But if you do something like, say, a cusp, then if you look at that place where it is not differentiable, no matter how much you zoom in there on your calculator, it's never going to look like a line. It's still always going to come to a point. So the idea is a differentiable function can be approximated by a line in a little small region. And of course, the line that we want to approximate it with is the tangent line, because that's what's going to fit there as long as we don't stray too far from the point of tangency. So that's the idea behind it. So, and then the rest of it is a lot of words and notation that can distract and confuse, but we can't let it do that. So I'm going to talk about a linearization. What I'm talking about with a linearization, I'm just talking about a tangent line. You can use a tangent line to a curve and approximate the values of that function close to the point of tangency with the line. So even if the function is something really exotic, as long as it's differentiable, then you can use that tangent line as a reasonable approximation around the point of tangency. That's what we're saying. So if f of x is differentiable at x equals a, then the equation of the tangent line which is written, I think, in a confusing form, L of x equals f of a plus f prime of a times x minus a, defines a linearization, defines what we will call a linearization of f at a. So that's the words and language that we use. It's called the linearization of f at a. And we say, you also hear it said, x equals a is the center of the linearization. So sometimes you will hear it said it's centered at x equals a. That just means that's where we're finding the point of tangency, is at x equals a. So the notation, I mean, don't be confused. It's easy to. Here's our curve, our f of x, and we are looking for a tangent line at x equals a. Well, so we run this thing up to the curve, and that means that this y value, because it's on f of x, the y value is going to be f of a. Yeah. And so the coordinates of that point, where we're going to find the tangent line that's on the curve that has x coordinate a, is a comma f of x. So that's just the x and y coordinate. That's how we're going to name the x and y coordinate. We know that the slope of a tangent line comes from the derivative evaluated at a. So we'll say the slope is, well, f is our function, its derivative is f prime of x, evaluated at a is f prime of a. So that's the slope of that line. Well, now, I mean, we have the point, we have the slope, so the tangent line is y minus y coordinate right, y minus f of a, is the slope, which we said is f prime of a, times x minus the x coordinate, which is a. Okay, so a lot of notation, but an old idea. So I add the f of a to the other side, so it's f of a plus f prime of a times x minus a. And then, just to further obscure things, we'll rename it as L of x. That's what we say. It's just a tangent line. It's just a tangent line. Okay, well, so you know how to find an equation of a tangent line. You know how to then use that tangent line to approximate values of a function. So let's do that. Let's say f of x is the square root of 1 plus x. And we'll say find the linearization of f at x equals 0. Okay, we're on it, so I like that. So we're really just saying find the equation of the tangent line at x equals 0. And then once we get that, that's part A, then we will use the linearization to approximate square root of 1.02. We agree on the tangent line?
Yep.
1/2 x plus 1? Nice. Now, here you have to be a little bit careful about what exactly is the role of x here. So if we want to use our tangent line to approximate the square root of 1.02, remember, this was our original function. What are we going to plug in for x? Yeah, 0.02, not the 1.02. So we're finding L of 0.02, and in this carefully constructed problem, that works out fairly nice to be just 1.01. Now, if you got your calculator handy, how good an approximation is that? Throw into your calculator, we'll assume this is going to be as accurate as we can. What is the square root of 1.02? 1.00995 and on. So, not too bad, huh? Not too bad. And granted, we didn't go very far from the point of tangents here, because we only went 0.02, 200ths away from the point of tangents. And that's the idea. It's not going to be a great approximation the further away you go.
Why is x only 0.02?
Because this is our original function. So what x value is going to make us evaluate square root of 1.02? It's easy to plug in 1.02 and that's not going to work. Ted, how we doing? Okay. Ted, we doing all right?
Yeah.
Okay, well, I'm going to jump on and then sprint to Newton's method. So the idea behind Newton's method is we're going to use the fact that a differentiable function is locally linear as a way of finding zeros. So if we have some curve f of x that does something like this, and we do this all the time on our calculator, where we graph something and then we use the second calculate find the zero. Our calculator, I don't know, I haven't found anybody to tell me definitively if Newton's method is what our calculator uses to find that zero, or if it's some kind of modified version of that. So I don't know if it's exactly Newton's method or something like Newton's method that it uses. So what we want to do is find out where does that thing cross the x-axis. Where is it zero? So what we do is we say, well, I don't know, so let's guess. So you start with a guess. I'm going to guess it's about whatever x of 1 is. Okay? So then we are going to run that up to our curve, and we're going to find the equation of the tangent line to the curve at that point. Then we're going to extend that tangent line until it intersects the x-axis. And we're going to say, there's our first approximation. It's the first approximation after our guess. We'll call it x of 2. Okay? Now, that may or may not be pretty good, but the idea is we can iterate this. We can do it again. So now we're going to take this point. So now what we did with our guess, we're now going to do with this point. We're going to run it to the curve. Find the equation of the tangent line to the curve at that point. Run it to the x-axis, and that's going to be a better approximation. And the idea is we can do that over and over and over and over again. And most of the time that works great, and we'll get pretty quickly a pretty accurate approximation to that zero. Okay? So here's what it looks like. So we have this first guess. So we're going to guess our x of 1. Then we're going to find the tangent line. Well, let's see. We plug in x1 into the function, so we get a y-coordinate of f of x of 1. And then we find the slope, and that's going to be the derivative evaluated at x of 1. And so then we're going to get our tangent line. Tell me if I'm going too fast, because I'm racing against the clock here. Y minus y1 equals m times x minus x1. So y minus f of x of 1 is f prime of x of 1 times x minus x1. There's our tangent line. We run that tangent line until we cross the x-axis. At the x-axis, the y value is 0. So we're going to plug in 0 for the y. So we have negative f of x of 1 is f prime of x of 1 times x minus x1. And now we're going to solve for that value of x, and that's going to become our x of 2. So I'm going to unravel it. So here's our negative f of x of 1. I'm going to divide by the f prime of x1. So now we have x minus x1 left. Okay? And I add the x1 to the other side. So I have x1 minus f of x1 over f prime of x1. And this I'm going to call x of 2. That's my next approximation. And I'm going to do the whole thing over and over again. So what I'm going to do is say x sub n plus 1, the next guess. My next approximation is going to be the previous approximation, x sub n, minus the function f evaluated at x sub n, that previous approximation, divided by f prime of x sub n the derivative evaluated at that x of n. And then we just do it over and over again.
Sounds good.
Sounds good. So most of the time, like I said, that works great, and you find it fairly quickly. Now, when you do it on your calculator, you're going to get your decimal approximation on your screen. Then you're going to do it again. And when you get decimal places that agree, then you know that part is correct. And you keep going until you get enough decimal places in agreement to give you the accuracy that you were directed to get to. 3 places, 5 places, 6 places past the decimal. Now sometimes things can go wrong, but not too often. One, if you end up with somehow your guess leads you to getting a derivative at 0 that's equal to 0, dividing by 0 is a problem. But that usually means I'll just pick a different guess and you'll get around that. But it can happen if we have, bad function is, and there's not much of a way to fix this, but we can, if you get something like a cube root function doesn't go well. You know where that's going to be 0. But if you make a guess and you come here, see if I can do this right. So you look at your tangent line and then you run that down to the curve and you get the tangent line and you can get caught in an endless loop. So it's not converging to anything now, it's just bouncing around. Or what's worse is, you'll start with a positive and it'll give you a negative that's further away. And then it'll give you a bigger positive and a bigger negative. And it starts careening out to, it's just not a good way to fix that. Why do you get to talk about differentials? Fortunately, there's some support videos on there. So you can still do that, and we're going to do, I think it's just homework 41. And there's a nice way, it tells you on the video, you can set up your calculator here, or you can just go enter, and it works out really slick. So when I go through that on the support video.
What's the name of the video specifically?
It'll say